Our next presenter is also named Mark, but his last name is Pavic. And he will be talking about his research work on how row widths affect potato crops. Mark is a professor in the Department of Horticulture at Washington State University. He also has been the state extension potato specialist since 2004 and conducts agronomic and variety development research. Thanks, Mark, for being here virtually, and I'm looking forward to hearing your presentation right now.
Good afternoon. My name is Mark Pavic. I'm from Washington State University in Pullman, Washington. Today I'm going to talk to you about research that was conducted over a 5-year period in the Columbia Basin of Washington State on potato row width. The title of my presentation is called Row Width Considerations for the Commercial Potato Producer. I'd like to acknowledge my co-authors Zach Holden, Rhett Spear, and Rudy Garza. They all assisted with this research and the presentation. I appreciate their efforts. So let's get after it. So why manipulate the spatial arrangement of seed potatoes? One obvious answer is you want to improve your income or your bottom line. And tied to that is improving land use efficiency. So you're going to get as much production per unit of land as possible, or perhaps income per unit of land. You want to optimize your tuber size profile for your market, which is also tied to your bottom line. So if you're growing seed or little potatoes or processing varieties, you're going to want to optimize the most valuable tuber sizes because after all, potatoes are bought and sold by size, not just yield. Or perhaps you have a current planting configuration issue where you're getting, say, perhaps bruise from tire rub, and you'll have to change your row width for your tires. Or perhaps because other people are doing it, it must be a good thing. What I want to show you with this slide here is that there's things we can predict when we plant seed pieces closer together. So whether you have plants at 8 inches apart or a foot apart, when you compare the two, we know that plants will respond differently. With narrow spacing, they tend to throw more tubers per acre because there's a higher plant population per acre versus wide spacing. But per plant, each plant may produce fewer tubers because they're sensing competition and vice versa. You also might expect these tubers to be smaller because they're closer together. So this is a trend that we can expect to happen when we change in-row spacing and perhaps row width. So this slide here shows with Russet Burbank when we did an in-row spacing study where we looked at 8, 10, 12, and 14 inches in row. And here we're looking at adjusted gross percent differences from the 8-inch in row and total yield. We can see that maximum yield was actually optimized around 9 inches. You know, you have a higher plant population, so you get more tubers per acre, and this resulted in a higher yield. However, when you take into account the value of the size profile, maximum economic return was actually at 12.5 inches. So your adjusted gross was optimized here, while your yield was optimized here. So what we want to do in all potato production systems is optimize our maximum return, not necessarily our yield. So, you know, if you're interested in maximizing your yield, you might miss the boat because your size profile, again, is very important because potatoes are bought and sold mainly on size. So we might ask, can we expect tuber number changes if we move our rows closer together? So here's 34 inches versus 36 inches. So if you increase your plant population by moving rows closer together, right away you're increasing your seed per acre. So perhaps you're going to increase also your tuber number per acre. You might ask, why do we even plant potatoes in rows? Why don't we just plant them like wheat and scatter them across the field? This is an important consideration. Traditionally, there are actually quite a few reasons why we plant in a row. Efficiently order use of space, guide equipment to avoid smashing potatoes, a place for your tires and harvester blades, a place for the planter, cultivator, and harvester to run, post-planting weed disruption if you use a cultivator or if you drag off, your tires need to go somewhere. Incorporating fertilizers and herbicides allows placement and incorporation on sides of the rows. Water drainage, perhaps, keeping the seed piece above excess water. Furrow irrigation, a lot of this has died out in the Columbia Basin. Most are now on pivots. A space for potato growth, hill enlargement, and increased seed piece depth through cultivation. And use of a dam or diker like they use extensively in the Columbia Basin for erosion prevention and to mitigate soil compaction. So now that we've determined that we need rows, How wide do we put the rows? How wide do we plant now and why? This is a good question. If we go back to when horses were used, we can see that horses had to walk somewhere. And they're on the yoke here is about 34 to 38 inches. And this is probably where a lot of our row widths got started. So if we look at row width across the globe, it varies. Within Washington State, we're at 32 and 34, although we've always been at 34 until I started doing the research. Some growers have now moved to 32. We do 22s or 17-inch beds or rows for little potatoes. Western Washington, they're on 36. Across the rest of the Northwest, it's usually 34 or 36-inch rows. But Canada, there's some that are 38. I would think this would mostly be dry land. But if you're irrigating and you're on 38-inch rows, I would think you could probably do better by going a little bit narrower, 36 or 34. But again, it'd be nice to have research in your area to determine that this is indeed true. In the UK, they do things a little bit differently. They're averaging 36 inches, but because they have large tires for destoning and declodding the land, they actually have to have room for the tires that are really wide. So they'll plant one row at 38 inches, then they'll be followed by 34-inch rows, and then a 38-inch wheel row. So it's a little bit different there. Most of continental Europe is using a 30-inch row spacing, using skinny tires and unique harvesters, which I'll show you on the next couple slides. So you can see here in Europe, they have very skinny tires, and I think this is in Holland. And they're able here, they have dualies on, I think they're 30-inch rows. So they're able to plant on 30s. For harvest, a lot of them use these self-propelled harvesters, where they have really skinny tires on front. The rear tires are inset, so they're not rubbing where the potato rows are. So you've got, this is where all the horsepower is pushing. And it's a really clever design in that they're not anywhere near the row. So the only tires that are near a row are those that are guiding the machine, and they're skinny. And they have a vine beater here. And I know a lot of people in the US and Canada don't use these, but there might be other options available. There are other options they use over in Europe and the UK, where they'll have an offset digger where the tractor drives where it's already harvested. And then there are no tires rubbing against the rows. The one issue we have here, though, is they're only digging 2 rows at a time. And I know a lot of these big operations in the Northwest here, that just isn't feasible. This one's actually in the US, where they were windrowing. You can see the very skinny tires here, and they windrow into the center row, and then they pick it up with the tractor here. One thing I don't like about this configuration is you essentially have a wheel on almost every row, except for perhaps the center one here. So what does that lead to? That could lead to bruise on every one of these. And it depends on how skinny your tires are and if you're using GPS or not, and a lot of other things. But I would say trying to keep tires against rows to a minimum is important, but you have to be able to do what you want to do. So sometimes this might be necessary. So the question is, are we as efficient with our land as possible? And when I started this research, 34-inch rows were standard, and they still are standard in Columbia Basin, Washington. And the question I had was, are 34-inch rows too wide? Because I could not find any research that said why we were on 34-inch rows. And so I wanted to find out why. And how does this differ by variety? There's a continuous need for efficiency, as you know, on a global market. And that's with land, water, fertilizers, crop protections, and everything that you do on your land. Conducting row width research is actually rather difficult, and on the surface it doesn't seem like it should be, but when you get into it, you realize you need a lot of equipment. So there's a lot of equipment involved. It's expensive. Changes to the equipment is time consuming. You have to have a tractor or multiple tractors that fit into the rows, planters, cultivators. All this has to be adjustable, or you have to have multiple copies of each that are the same generally overall, so that you're comparing apples to apples. Cultural management, you could increase irrigation and fertility, although in this experiment we did not do that. We wanted to see if we were utilizing land and inputs as efficiently as possible. This could be another study in the future. Cultivating the rows, for weeds and using dam or dikers. Those also have to be adjustable, or you don't use them in the research. So it's a little more difficult that way. So the row width study that I conducted was across 5 years. It was planted near Othello, Washington on our WSU research farm. Over the course of the years, we looked at 9 varieties. We ended up looking at the main varieties at the end, the big ones like Burbank, Umatilla Ranger, Alturas. But we also looked at ones like Chieftain, Teton Russet, Yukon Nugget, Mountain Gem Russet. We did not focus on in-row spacing. So when we moved our rows closer together or farther apart, we didn't care about the in-row spacing in that we didn't adjust it. So we kept it consistent. I wanted to know if everything was the same, just how row width played a role in our yield, economic return, and growth and development. So from 2011 to 2012, we looked at 30 to 36 inch rows with 2-inch increments in between. We found out that 36 was indeed too wide for the Columbia Basin, and we're glad that we're not planting on 36s. So we adjusted that to add 28 inches in 2013 and 15. Today I'm going to show you data primarily from 2013 through 15, where we looked at 28, 30, 32, and 34 inch rows. So when you look at plant population, 28 inches came out to be, and this is at 10-inch in-row spacing, 22,400 plants per acre. And then compared to our standard 34-inch rows within the Columbia Basin, that's 21% higher plant population. 30 inches is 13.3% higher, and your 32 inches is 6.3% higher than 34 inches. And your 34 inches produces, or we have around 18,500 plants per acre that are the result of planting that many seed tubers. So the idea was to use the same level of inputs: fertilizer, fungicide, irrigation, pesticide, and ultimately irrigation. Although I think that perhaps maybe we should have tried to irrigate a little heavier, and I'll show you why. So if we move our rows closer together, we're going to add more seed per acre just by doing that. And so we have to take into account the cost of the extra seed when we're looking at our economic return. So to do that, we calculated that based on $20 a hundredweight, a 2.5 ounce seed piece, and this price is cut and treated seed at 10-inch in-row spacing. So that added $124 per acre for the 28-inch rows, $77 for 30, $36 for 32-inch rows, and $0 for 34-inch rows because that was our standard. When you move your rows closer together, you're going to experience additional costs, variable costs per acre for fuel, equipment, depreciation, and labor, and a few other things because you're adding rows to each acre. So at 28 inches, we'd add actually 15 rows per acre. 30 inches, we're going to add 10 rows per acre. 32 inches, we'll add 4 rows per acre. And I calculated the additional variable cost to be about $225 per acre, or about 5% of the production costs. So if you look at the extra tillage acres created by those rows, and you times it by the price per acre, you get the additional variable costs due to extra passes made with your equipment. So you'd be making extra costs or extra passes with your equipment. It'd cost you about $38 more with 28-inch rows than at 34s, $27 for 30-inch rows, and $11 for 32-inch rows compared to 34-inch rows, which would not cost you any more because that's your standard. Here are some photos of my team planting the row width studies. And we actually ended up using this planter the most. It was hydraulically adjustable. And the seed pieces are hand fed in through the system there, so we don't have any planter skips. And they're all spaced very accurately apart. We also use a GPS tractor so that we were perfectly straight with our rows. So let's jump into the results. First off, we'll look at average vine length. And during the time period where we looked at 30 to 36-inch rows, we actually measured the vine length. We didn't do it later on, but what we found was as your rows move closer together, the plants grow longer vines. And the reason for that, I believe, is because the plants sense the competition and they're trying to get their vines longer so they can gather more sunlight. So they're trying to get out past the other vines whereas when you're wider apart, your vines are smaller. Here, if we look at average tuber weight, this is average across 3 years and the 6 varieties, with average weight on the side here, and then the row width. We can see that average tuber weight did not really vary much, and this is largely because the plants adjusted to the competition and they shifted things around in terms of tuber number per plant, which I'll show you a little bit on the next slide. So here you can see average tuber number per plant, again averaged across 3 years and 6 varieties. Tuber number per plant increased as the rows were wider and vice versa. So when the plants sensed the competition, they produced fewer tubers per plant and vice versa. And this is common, like I showed you on some of the first slides there. So harvested tuber number per acre did not really change much across the different row widths. And this was because the plants adjusted by producing more or fewer tubers per plant. So to some degree, these plants sense, the competition, and they'll do what they can to produce almost the same number of tubers per acre. This is not always the same. When we look at in-row spacing changes, this typically doesn't hold as strongly as it did for this row width study. One thing we looked at and we had questions about were how did green tuber number or the percent of total yield change when we moved rows closer together. And what we found was there was no significant trend. Although at 30 inches there was numerically a higher percentage here, but I think this was kind of a quirk because at 28 inches we didn't see any change here either. So we really didn't see an increase in percent of green tubers as far as total yield goes. So here we have percent difference in total yield per acre compared to the 34-inch rows. And again, this is across the same varieties and the same time period, where we have Burbank, Alturas, Ranger, Norcota, Umatilla, and Chieftain. And here 34 inches is a 0 or flat because that's the one we're comparing to. When you take a look at 32 inches here, all varieties liked being at 32 inches. They increased their total yield. 30 inches was similar, but not quite as dramatic across varieties. At 28 inches, we actually had some varieties like Burbank, Umatilla, and Norcota that did worse than at 34 inches. I think this is because lack of water. So as you increase your plant population per acre, more plants, they're going to require a higher volume of water per acre. And I think in our study here, even though we were doing our best to monitor it, I think these got dry and the yields were reduced because of that. Here we're looking at total and market yield a little differently, average across those varieties for the 3 years with a nonlinear regression model. And what we can see here is that the peak was probably right around between 30 and 32 inches if this model predicts where we maybe didn't have a treatment. But if you look at the actual data points, yield was pretty high at 32-inch row width. And one thing I want to comment on that I did before is perhaps here, if we had more irrigation, this line would have been more of an upward trend. But at this point, 31 to 32 inches looks pretty good for yield. I want to point out Chieftain. This is a specialty variety in that it did continue to increase in yield pretty much from 34 up to 28-inch row width. And it is one of these varieties that does very well in the Columbia Basin if you plant it close together. And so it was kind of an exception to the rule there. One question we have when we move rows closer together, so a tighter row width, is do the larger tubers get smaller? Do we have less large tubers? And this looks at that. So this is average across the varieties here at top. We look at total yield here on the graph, greater than 6-ounce yield and greater than 16-ounce yield. What we see is it really didn't change as we planted closer together. Plants are adjusting tuber number per plant, and what we saw is actually at 32 inches, got a little more of a bump in size profile for greater than 6-ounce yield. But the greater than 16-ounce yield really didn't change much until you got to 28 inches. This looks at tuber yield per plant. So it's actually pounds per plant and across the different row widths. So if you harvested every plant out of those rows, each plant would weigh this much. So here we got 3 pounds and close to 4 pounds for these. So this just shows you that tighter row width here did not reduce weight per plant. And so if you're planting at a closer row width, you have more plants per acre. So this will actually equate into a higher yield per acre because the tuber yield per plant did not change. When we planted closer together, we actually got an increase in specific gravity. And as I've mentioned before, I think at these higher plant populations, there was just less water to go around, and that caused tubers to have actually less water content at final harvest. So that's one theory there. But I don't know if it was much to do with actually plant physiology other than just a higher plant population per acre. So if we look at percent difference in seed cost adjusted gross return, so this is grower return, compared to 34-inch row, where 34-inch again is 0, we see here that 32 inches was best across all treatments when you take into account the extra cost of seed. And this is by variety here. And 30 and 28 inches actually saw some loss. And again, I think that might be somewhat due to lack of irrigation, but it could also be due to the fact that 32 inches was better, and so is 34 inches. So here, at least, we're being told that 32 inches is the economically best returning row width. And this is seen again with the nonlinear regression, and it predicts the same thing, around 31 to 32 inches is probably best when averaged across these varieties. This is for the processed market. So for North Dakota, where we looked at the fresh market, we saw a similar trend again, and it was around 32 inches. Additional information, none of these factors were affected by row width changes: hollow heart, brown center, internal brown spot, tuber shape, black spot bruise, or shatter bruise. So in summary, reducing row width in Washington is feasible where we have irrigation, water is non-limiting, and we have a long growing season. Inputs stay the same other than irrigation, and it looked like by doing that, we came out just fine. So I think this is a more efficient use of our land and our inputs. It was stable across varieties in time, and this was with larger indeterminate varieties, with indeterminate vines like Alturas and Ranger, also with weaker determinate vine plants like North Dakota and Teton russet, and then intermediate indeterminate vine types like Burbank, Umatilla, Mountain Gem russet, and Chieftain. So we saw a net gain of about 3 to 5%, or $100 to $300 per acre conservatively, and about a 3% yield boost by switching from 34 to 32-inch rows. So in the Columbia Basin of Washington and Oregon, 34-inch rows appear to be wasteful and inefficient compared to 32 or 30-inch rows. Plants were able to sense competition as rows were spaced closer together, and they adjusted by plant or tuber number per plant. This was at an in-row spacing of 10 inches. Most varieties produced better dollars per acre at 30 inches than 34 inches, and the same was at 32 inches, but I wanted to indicate that there were more than just one row width that worked better. Growers switching row widths should plant test strips if possible. They should consider equipment changes. Tractor tire width is going to be important. Equipment costs. Perhaps you want to depreciate out planters and harvesters and then switch, so wait until they're worn out. You need to consider equipment needs on other crops, so your tractor width, tire width, is going to be affected possibly, so your other crops, you may have to change things. One size does not fit all. Row width and spatial configurations vary by market and depending on the variety you're growing. So improving land use efficiency is likely possible for most growers. Optimal plant spatial arrangement is likely different by market type, as I mentioned. And there's also another factor you could consider, and that's bed planting versus rows. That's another dimension. I can't get into that today, but it's a consideration. Most systems can be improved, however. On-farm row width research is difficult. Do what you can, however, but it'd be nice if you could find a researcher in your area that would be able to do this on small plots, so you don't risk financial loss. Soil water is likely a limiting factor, and this may not work on dry land. If you have an irrigation system where you can apply as much water as you wish, this may work for you. Dry land, you need to consider how much water is available to each plant before you do this. With that, thank you.
Thanks, Mark. I think I may have to write a story about that for Spud Smart.